We do have the case of compounds that contain polyatomic ions. And polyatomic, just like it sounds, means many atoms that form an ion. They contain more than one atom, just as we said, and often we can identify these because they're in parentheses when we write our formulas, if there is more than one of them present. The name and the charge of the polyatomic ion do not change. So the name is going to always be the same name for that arrangement of atoms, and the charge will also always stay the same. And we name these compounds that contain polyatomic ions by naming the cation first and then naming the anion second, just as we've been doing, but now with the name of the polyatomic ions. There are lots and lots of polyatomic ions. There's few that we will see over and over again. The ones that are highlighted in pink are polyatomic ions that will be used quite frequently. These include acetate, which always has a -1 charge, carbonate, which is always 1 carbon, 3 oxygen with a -2 charge, hydroxide with an OH-, nitrate, NO3-, phosphate, NO4 with a -3 charge, ammonium, which is the only common one that we see with a positive charge, which is NH4+, permanganate, MnO4-, and sulfate, SO4 2-. We are going to see these over and over. If you have them memorized, it will save you some time looking up their formulas. Naming an ionic compound that contains a polyatomic ion is just the same as naming our ionic compounds. So we're going to start by identifying the ions. We have Na and we have SO4. So SO4 always has a -2 charge. We name the cation sodium. We name the anion, which is sulfate. So do notice that the ending is different. Before, when it was just an S, it was sulfide. SO4 2- is sulfate. The ending is different. IDE versus ATE. Because there's oxygen, it ends in the ATE. Our name would be sodium sulfate. If we're naming a polyatomic compound and it contains a transition metal, we still follow the same rules. We identify the ions, so we can find that iron has a -3 or has a +3 charge because nitrate has a -1 and there's 3 of them. And nitrate always has a -1. Can name the cation, iron 3. We need the Roman numerals because this is a transition metal and its charge can change. We name the anion. Again, you'll notice that it has that ATE ending, which is different than nitrogen by itself. And we write the name of the cation followed by the anion, iron 3 nitrate. Name the following compounds. Pause the video and write their names. The first one, we have NH4. This is our positive polyatomic ion. So we would have to write this as ammonium. Its charge is always +1, so we do not need to include it in the name. Cl is chloride. We go to the next one. Ca is in the second column of the periodic table. We do not need to include the charge because calcium's charge is always +2. So calcium, if we look at our polyatomic ion, C2H3O2, his name is acetate. So this would be calcium acetate. The last one, number 3, copper is a transition metal. We need to figure out its charge. Nitrate is always a -1. There's 2 of them, which would give us a -2 charge total. That means because we have 1 copper, that the charge on copper would be a +2 to balance the negative charge. NO3 is nitrate. Writing the formula from the name, we're going to write the symbol for the cation and its charge. Here we have iron 3. The symbol is Fe, and the charge is given to us in the name. We write the symbol for the anion, phosphate. So phosphate is always PO4 with a -3 charge. Now we're going to write our formula by making the charge the subscripts. We would get Fe3. Now if you have more than one polyatomic ion, you do need to put it in parentheses. That way this tells us that we have 3 of the entire group. So 3 phosphoruses and 12 oxygens. We can reduce this, however, so this is not our final formula. We can divide the subscripts by 3, and we would end up with iron phosphate. If we only have one polyatomic ion, no parentheses are required. Check the total charge. Our iron was a +3. Our phosphate was a -3. Those charges balance. Try writing the formulas from these names. Pause the video. Aluminum is Al3+. Sulfate, it ends in ATE, so it's going to contain oxygen. SO4 2-. If we make the charges the subscripts, we end up with Al2. We need parentheses. SO4 3. About chromium 2 carbonate. Chromium, it's a +2. Carbonate is a -2. So we end up with CrCO3. Hydrates are a special class of compounds which are still ionic compounds, but they have water incorporated into their chemical structure. And there's a very specific number of waters for each formula unit. We refer to the ionic compound as a formula unit. Now this is a reversible process. We can drive off the water by heating it up and evaporating the water off. The formula that shows that the water is attached to our compound has a small dot in between the ionic formula and the number of waters. To name these, we add a prefix that tells the number of waters plus the word hydrate after the ionic compound name. So if we had COCl2.6H2O, it would become cobalt 2 chloride, hexa meaning 6, hydrate. If we had CaSO4 1/2 H2O, it would be calcium sulfate hemihydrate. The prefixes that you're going to use are located in the table. Hemi is half, mono is 1, di 2, tri 3. You can think of it like shapes that you learn in math. So triangle, it has 3 sides. A tetrahedral has 4 sides. Follow that pattern. They do have different colors and slightly different properties depending on if they are the hydrated compound or the anhydrous. Anhydrous means without water. Many of the ionic compounds will easily absorb water from the atmosphere, forming hydrates. Here's the practice for the hydrates. Write the formula or the name. Pause the video. Magnesium is a +2, sulfate is a -2. So when we combine these, it becomes MgSO4. The heptahydrate, hepta means there are 7, and hydrate means waters. So our formula would be magnesium MgSO4.7H2O. What's the name for NiCl2.6H2O? Well, Ni is nickel. We know that it has a +2 charge because of the chloride. This becomes nickel 2 chloride. We do need the charge because nickel is a transition metal. 6 is hexa, so it becomes nickel 2 chloride hexahydrate.